In this video, we're going to continue our discussion about motors and controls by talking about the servicing and the troubleshooting of electric motors and controls. For those who have a Modern Refrigeration book, 20th edition, this goes along with Chapter 17. The objectives of this presentation is to figure out how to use different testing instruments to measure electrical variables in a circuit. We want to be able to test motor winding installation using a Megohmmeter and perform maintenance based on the measured resistance. You want to be able to determine the cause of motor troubles by checking a motor's current draw, start, run capacitors, and internal temperatures. You want to be able to measure three-phase motors' voltage and winding resistance to test for single phasing. We want to be able to use an ohmmeter to take measurements on a Hermetic compressor motor and determine whether it has a shorted winding, an open winding, or short to ground. We want to be able to start a stuck compressor motor by connecting a hard start kit to the compressor terminals. We want to be able to service fan motors by identifying connection problems, fan problems, and electronically communicated motor trouble codes. We want to properly lubricate motor bearings and install belts connecting external motors to belt-driven units. You want to be able to troubleshoot and replace faulty control system components such as thermostats and motor starting relays. The first source of our troubleshooting most often has to do with a voltmeter. A voltmeter measures the potential difference between 2 points in a circuit. They're analog or digital. They're always connected in parallel with a load in a circuit. So if you want to measure the voltage across a power source, you're going to connect your meter in parallel. The same as a heating element. If you want to measure the voltage across a heating element, you're going to connect your meter in parallel. Okay? Always in parallel with the load. Alternating current, it reads the voltage without regard to polarity. Lead placement is not critical. In other words, there's no positive or negative. Direct current, it does matter. Place the black lead closest to the minus terminal and the red lead closest to the positive terminal. Direct current lead placement matters. Ensure the leads are in the correct meter jacks. Many meters have numerous jacks on the end. Make sure it's in the correct meter. Set the range switch to the correct range. Most of our meters are now auto ranging, but always know if your meter isn't. Residential HVAC applications are normally 120 or 240 volts AC. Low voltage circuits, 24 volts AC. Electronic circuits might be 1 to 25 volts DC. Okay, so always set the range switch to the correct range. If you have an auto ranging switch, use it. Always set the voltmeter's range switch to a higher voltage setting than expected from the circuit. It prevents meter damage in the case of a voltage surge or higher than anticipated voltage. Again, if you have an auto ranging meter, use it. An ohmmeter measures the electrical resistance in circuit. It checks for short circuits, open circuits, shorts to ground, high resistance connections, and it's always connected in parallel with the load. Turn off and lock out a circuit's power before taking resistance readings. When voltage readings take a voltage reading across switches and electrical loads in series with an intended resistance reading to ensure there's no voltage present. An applied voltage may ruin an ohmmeter. You also want to, even though it doesn't say it here, you need to isolate the component that you're taking a resistance reading of. Okay, in other words, back here, I would not want to take my resistance with it in the circuit. I would want to remove the switch from the circuit, remove the heater from the circuit, so I'm not picking up the resistance of the rest of the circuit. Okay, always isolate the component that you're taking the resistance of. Resistance across an open switch would be infinite, or OL on the electronic meters. Resistance is so high the measurement cannot be measured. When checking continuity, we're looking for 0 ohms. If you get 0 ohms, the conductor's not broken. The connections are good. If a meter reads infinite or OL, check for an open switch, broken connection, or other cause of high resistance. Voltage resistance across any load that's good will give you some number. Resistance across a bad load would give you OL. An ammeter measures current in amperes. Circuit must be on and operating to measure current. You have two types. You have a clamp-on meter and you have an inline meter. Most HVAC electrical work can be performed with using clamp-on meters. Okay, and always make sure your meter is rated for the amperage you're going to draw if you use it inline. Clamp on, the clamp just clamps around the wiring, okay, like here. The clamp on ammeter, it's not necessary to disconnect wires or attach leads. It measures the current based on the magnetic field produced by the AC current. Jaws should only enclose one wire in the circuit. Do not put the jaws around the like L1 and L2 or L1 and neutral. They'll cancel each other out. Only put it around one wire. Inline, you're actually putting your amp meter in series with the circuit. So you have to shut off the circuit, put your amp meter in line, and then turn the circuit back on. Lead connections must match the polarity of the power source in a DC circuit. The black lead is closest to negative terminal, red lead closest to positive. If you're doing it in an AC low voltage circuit or low amperage circuit, it doesn't matter. A multimeter, which most technicians use these days, measures multiple variables. Measures voltage, current, resistance, also called a Voltmeter, VOM. Other functions most multimeters have is a diode check, continuity check, capacitance, induction, frequency, temperature, and it has attachments for other readings. So again, multimeter settings, always look at the manual before you use a meter. It's pretty important so you know what meter you're using. Diode check, the multimeter shows whether or not a diode is functioning. It shows the amount of voltage conducted across the terminals. You check a diode using both lead configurations. If a diode is functioning, if it shows voltage, when the red lead is connected to anode, black lead is connected to cathode. Continuity checks for a continuous unbroken path between 2 points in a circuit. In other words, a closed circuit. Often we use audio confirmation. The multimeter beeps when continuity exists. No beeping means the circuit is open. Frequency checks the cycles of the AC current per second. Most AC in North America is 60 Hertz. Sometimes we use special frequency in the case of variable frequency drive or VFD motors. For multimeter use, we verify the load is correct, receiving the correct power at the correct frequency. It verifies 60 Hertz line circuit. My meter that I use most often tells me immediately what the frequency is anytime I'm using it in amperage mode or voltage mode. Okay, it's sort of important to know that the equipment is getting the correct frequency. There's additional options for most multimeters. You might have a thermocouple attachment for temperature measurement in the form of a probe, clamp, or strap-on temperature measurement. You can also get airflow attachments, relative humidity, luminance, that's light, or acidity or alkalinity, that's pH. You can have a power factor and a wattmeter. The power factor meter provides direct readings of power factor. It's a relationship between true power and apparent power. It's a ratio of wattmeter reading calculated power. Wattmeter measures the true power wattage of a circuit or load. It's connected in series with the circuit. It's to use to confirm that the load is operating at the correct power level. Electrical insulation testers are available. It's called an AKA Megohmmeter. It's most often used on motor windings. Some multimeters actually include this internally as a part of the resistance readings now. It measures the resistance by applying a known voltage. The results, if there's less than 100 megohms, may indicate a problem. Lower readings may indicate moisture and contamination. And this chart actually is pretty neat because it shows the difference in insulation resistance measurements. That's megohms. Over 100 megohms, we have excellent insulation. No action is necessary. This is talking about a compressor. 60 to 100 megohms, you have some insulation breakdown, some moisture is present. What you want to do is change the filter dryer and, if possible, clean and dust debris from the windings. You usually can't do this. 40 to 60 megohms, you have overheated windings, contaminated oil, and moisture in the system. Change the filter dryer. Check the oil for burnt odor. If there's no odor, oil is contaminated and needs to be changed. 20 to 40 megohms, you have severe contamination. The system's going to fail soon. Change the oil, filter dryers, and if old oil has burnt odor, check the system's motors, including fan motors, for worn bearings. You have overheating that's occurred. To determine motor conditions, listen. Your ears are a pretty important form of troubleshooting. Measure the unit's current draw. Measure the locked rotor amperage and the full load amperage. Observe the length of operation. Okay? For a Hermetic compressor motor, 120 volts, here's some normal readings. For a 1/4 horsepower, at 70 degree ambient temperature, you're going to be pulling 235 watts. For 110 degree ambient temperature, it's going to rise to 320 watts. Okay, anything over these numbers can indicate a problem. Motor capacitors are pretty important too. They do go bad. Run capacitors are filled with oil to dissipate heat. They operate whenever the motor's running. Start capacitors are dry. They're electrolytic capacitors and they're only used for motor startup. There's a bleed resistor on most start capacitors that discharge the capacitor when the motor is off. When you look at the run capacitors, look at the ratings stamped on the manufacturer. You'll have a microfarad rating, you'll have the manufacturer, and you'll have a model number. Never place your fingers across the terminals of a capacitor. To discharge the capacitor, you're supposed to put it in a protective case and discharge it through a 30K ohm resistor connected between the terminals. Do not short it with a piece of wire or screwdriver. Do not open the shell of a capacitor filled with a liquid. It's a PCB liquid. Okay, that is hazardous to your health. Motor temperature is the temperature of the hottest part of the motor. It should be no more than 72 degrees Fahrenheit above ambient. Generally, it runs about 150 degrees Fahrenheit. But again, no more than 72 degrees above ambient. The rated ambient temperature is listed on the nameplate. Maximum ambient temperature at which the motor can operate. So again, take a look at the ambient temperatures. It's very possible that your ambient temperature, remember that's the air temperature surrounding the object, could be higher than what the maximum ambient temperature at which the motor can operate. Keep motors clean and free of dust. Dust is an insulator. It can affect heat dissipation. To measure the motor temperature, use an infrared thermometer. Aim it at the motor frame. Okay? The internal temperature of that motor will be about 20 degrees higher than the motor frame. If you have excessive temperatures on a motor, look for short circuits and current overloads. Single phasing of three-phase motors is a problem. Single phasing is when a three-phase motor loses one or more phases. Remaining phases pull more current and may overheat and burn out. Many systems, especially newer higher-end systems, includes a phase loss monitor. It monitors the voltage of each phase. It stops the motor when one phase goes bad. It prevents motor damage. Testing for a single phase, all three sets of windings should have the same resistance value. Okay, so you disconnect the motor totally, and you measure the resistance across all three windings. should all have the same resistance value. To test single-phase hermetic compressor motors, turn the motor power off. Measure the resistance, and again, remove the wires from the terminal. Okay, you can't have anything in parallel with it. A lot of times the condenser fan is wired in parallel. So remove the wires. Isolate that motor. Measure resistance between each pair of terminals, between common start, common run, start, run. Check motor windings for continuity, shorts, and shorts to ground. Okay, and you do that by measuring between each terminal and the compressor shell. There are some standards for compressor winding resistance that are pretty important. If the motor horsepower is a half horsepower, between common and run, you'll get roughly 4.7 ohms. Between common and start, you can get 18.6. Between run and start, you can get 23.3. And for a 1 horsepower, that will change. As the horsepower decreases for the most part, okay, or I'm sorry, as the horsepower increases for the most part, your resistance on your windings will decrease. And these are rough numbers. Sometimes this changes based on what's going on in the factory. So again, you're doing, if you normal operation, okay, you will have between start and run, or I'm sorry, yeah, start and run will be your highest resistance. Common to run will be your lowest. And start to common will be in between. If you add your start to run together, okay, if you add these two numbers together, you will equal what you've measured from run to start. Okay, anytime you get an infinite or an OL across one of the windings, it means that that winding's open. If you get a much lower resistance across a winding, it means there's a shorted run winding, okay, in this case. So we have a 0.5. I don't expect a 0.5. That's going to be a shorted winding. There's something wrong with that winding. Okay. If I ever get a resistance from any of the windings terminals to the shell of the compressor, it means there's a short to ground. Sometimes motors can get stuck, okay, and inside a compressor you can't manually force the motor to get unstuck, okay. The reasons for this occur, okay, is settling of dirt or contamination, starting up a system that has been shut down for a long time. You can have excessive liquid refrigerant, especially in the northeast part of the country, where the refrigerant migrates to the compressor, and if there's no compressor crankcase heater, the liquid refrigerant will stay in the oil, and you can have electroplating. Okay, one of the things we can use to get a stuck compressor motor started is a hard start kit. It will be a capacitor, a PTC or a potential relay, and wires. It adds start capacitance to a system. There's two basic types. You have a 3-wire hard start kit and a 2-wire hard start kit. The 2-wire is the easiest to wire. You're going to connect the wires to the start and run terminals. Usually you can do this right across the capacitor, the run capacitor, which is in the system. Okay, you're going to connect the wires to the start and run terminals. The 3-wire hard start kit has a potential relay. Okay, the black wire connects to a common terminal, red and white wires connect to run capacitor. Puts that other capacitor in series. It is very important to always look and make sure that these have directions for how they are to be mounted. They do not work if they're mounted upside down sometimes or sideways. Always check. Common causes of fan motor problems: loose or dirty connections, dry bearings, worn bearings, burned out motor, loose fan, out of balance fan blades touching the housing. This is going to be your noisiest. Okay, and you have to check that with the motor running. Sometimes it doesn't do it if it's not running. Connection problems: loose or dirty connections and wiring increase resistance. It causes excessive voltage drop at the motors, causes loss of speed, it will give a loud humming, and it will overheat. You want to use your ohm meter with the system shut off to locate the faulty connection. Fan problems. If there's a loose fan, tighten the set screw that fastens fan hub to the shaft. Hub loose or broken from the blade. You have to replace the fan blades. Blades out of position, they could be vibrating. Replace the fan unless balancers are available. Usually it's to replace the fan. Balancers don't always work. Misalignment. Okay, the motor's not quite in alignment. Move the fan on the motor shaft and move fan housing. ECM motors, electrically communicating motors, are more and more prevalent these days in HVAC, especially with indoor blower motors. Okay, you sometimes have trouble codes that show up on the circuit boards that provide the control for these. Okay, but measure the voltages going to the ECM motor. Okay, make sure on the 120 volt side it is getting power. Confirm communicator between motor and controller. Check wiring. Look for loose connections. And then follow diagnostic charts and manufacturer recommendations. Most of these motors have charts available on how to troubleshoot them. Okay, and sometimes there's motor testers available, especially for the GE motors. You can get motor testers. External motor electrical problems. Okay, external motors are used in open drive applications. Replace the motor if there's an open winding, shorted winding, or anything shorted to ground. If the motor will not start but hums, check the start capacitor. Check the motor started relay. If the centrifugal switch is serviceable, check that and make sure it's closing. Centrifugal switches are mounted inside motors most often, usually against one side of the drive. Okay, if it's available, check to make sure the spring is not deformed or the switch is not out of calibration. Some motors, especially the larger, more expensive ones, will allow you to replace that centrifugal switch. Smaller motors will not. Okay, it's if the centrifugal switch goes bad, the motor's bad. Check for worn bearings. Check for excessive end play. That means, can you move the shaft around by hand? Can you grab the motor shaft, wiggle it from one side to another, pull it in and out excessively? Okay, check for excessive vibration, and on larger serviceable motors, check the air gap between the rotor and the stator. Motor lubrication is extremely important, okay? There are either bushings, okay, that are over here on the side. Okay, there's bushings on the shaft. Okay, bushings are cylindrical sleeve bearings. They reduce friction and wear on the motor shaft. Bushing lubrication is done either with a Wick system, an oil rings lubricating system, or an oilless brush bushing. Wick lubrication systems, okay, actually push a wick that allows the oil to flow up onto the bearings. Okay. Yarn wick uses a yarn, okay, more of a yarn material that does the same thing, okay, keeps the bushing with a film of oil on it, okay, and there's always a seal on the end to prevent the oil from running out. Slip ring lubrication systems again have a bushing that's around the motor shaft but has a slip ring. What the slip ring does is it actually splashes oil. It pulls oil up as the shaft turns. Ball bearing lubrications, okay, many are sealed and do not need lubrication. Others might have a Zerk fitting. A Zerk fitting is this little grease fitting that you see right here. Dry bearings cause a noisy motor. Bearings will either seize or wear badly. Bearing wear can cause excessive end play, knocking, and extremely hot motor shaft. Again, what we're talking about end play, we're talking about the ability to manually move that shaft in any direction. Causes of overheated bearings: the oil could be too heavy, oil could be too thin, could have dirt in it or it's contaminated, could have belts that are too tight, could have a pulley hub rubbing against the bearing, and the motor could not be properly aligned. So let's talk about the types of pulleys. Okay, basic pulley, it's a grooved wheel with two flanges. Multiple grooved pulleys, variable pitch pulleys exist. Pulleys change rotational direction. They can increase or decrease rotational speed based on size, and they can provide what we call a mechanical advantage. Mechanical advantage means that if we're using a smaller size motor, we can turn extremely heavy loads by changing the size and rotation of our pulleys. The V-belts are measured by outside length. And then there's a cross section measured at the widest point. We have four types of V-belts. Okay, these are the belts found on belt drive motors. We have a classical, we have a narrow, we have a notched. Okay, these will have notches on the bottom, and we have a very small one for light duty. These come in, the sizes are designated by letters. Okay, so an A belt will be 1/2 inch wide at its widest point and be 5/16 tall. An E will be 1.5 inches wide at its widest point and 29/32 inches tall. Oops. When you're installing belts, you have to check for proper tension. The proper tension is the lowest tension at which the belt will not slip under full load condition. Best thing to do is use a commercial tension gauge. Okay, you can sometimes check tension by pushing down on the belt. And it shouldn't go down more than, I think it's a 1/2 inch, but just best way to do it is commercial tension gauge and compare it to manufacturer recommendations. The alignment of the belts are extremely important. The center line of the shaft parallel with the center line of the motor. The pulley grooves have to be in alignment with each other. Cannot be pulling the belt at an angle. Electrical connections are important as well. Make sure they're correctly installed. Okay, electrical connections need to be clean and tight. Wire terminals have to be large enough to carry the load. Wires have to be sized properly to carry the current. And the sensing elements have to be mounted correctly. Okay, so it's very important to make sure that the wiring is connected properly. If it's a terminal type post, okay, the wire lead needs to come in and be under the screw. Okay, it needs to be completely under and not pulling. The same thing with a heavier amperage nut connection. Okay, your terminal is gonna come under the washer and against the insulating terminal block. To troubleshoot thermostats. Okay, but this is a main troubleshooting point in refrigerators, coolers, and freezers. Make sure there's no contact corrosion. Make sure there's no overload. Make sure the bellows and diaphragm still have a charge. If you see bent pipes on the sensing element, if you see a bent cap tube, it won't work. Okay, make sure the sensing element is installed correctly. Thermostats for heating and cooling systems in residential and commercial buildings. If it gives you a trouble code, identify it. Use the manuals. Check electrical connections and verify continuity. Check switch operation. Check temperature sensing device. Make sure they are mounted in a place where it's actually sensing the room temperature and not outside temperature. You don't want them on an outside wall. You want to make sure the hole for the thermostat wires is not big enough where it's pulling in air from the attic or the basement. To troubleshoot relays, you want to replace defective relays. You want to use duplicates or a replacement chart or guide. In other words, you need to replace relays with a similar relay. Check for loose connections on start relays, capacitor, and related wiring. To replace a relay, disconnect the power supply. Label each wire as it's disconnected or make sure the schematic is correct. Keep the cover in place to avoid dust on contaminated contact points. Do not tap a relay to check. If it isn't working, it's not going to work. Make sure they're level and in the proper orientation, especially for current sensing relays.